I don't know, yesterday morning, block one, there was this like weird clicking, and we're looking around, and then we noticed that that whole like light fixture row was kind of oscillating. And I think there was just something going on with the bulb. The bulb was out now. It also could have been the fan. This morning the fan was clicking a little bit, and there could be resonance between the fan and the row of lights. It would actually be, I would have preferred it happen in here, but I was a little bit nervous. So if we hear that, let's identify that. So our next objective was a second look at the stability, the relative stability of nuclei. And we do have a graph that we often look at to help us talk about the stability. And that graph would be a plot of the neutron number, the neutron number, the number of neutrons, versus the number of protons. Okay, so I'm going to put that plot up. So it's here, probably doesn't show up tremendously well, but this is the number of neutrons on the y-axis, and the number of protons on the x-axis. And then there is a dashed line, kind of down here, and that dashed line just represents a slope of 1. Yeah, Jamie, that's fine, or if the other side of the desk might work also. That represents a slope of 1, meaning that we have the same number of neutrons and protons. Right? We kind of have this like misconception that stable nuclei have the same number of neutrons and protons. And I think we just have that misconception because of the elements that we're most familiar with. What are the elements that you would argue that you're most familiar with? Like, you could tell me the atomic number without looking. Hydrogen we're certainly familiar with, and who else? Oxygen, who else? Carbon, helium. Yeah, let's actually stop there. Those probably would be almost all of our, the elements that almost all of us could say the number of protons, and probably the most common isotope as well. All right, so we're going to come back to that. So this slope of 1 line is down here. The green section is showing us nuclei that are quite stable. And then the red ones underneath and above are quite unstable. And then really anything beneath the lower red or above the upper red just doesn't even exist. Like, it's so unstable it doesn't even really exist. And one observation here is that for our lighter nuclei, the stable ones are very close to our n equals z, our neutrons equals protons line. But as we get bigger and bigger nuclei, right, the stable nuclei are quite different from the number of protons equaling the number of neutrons. So let's look at these ones, but then I want to look at some heavier ones too, and we'll talk about why the heck this is. So hydrogen has how many protons? 1. And usually has how many neutrons? Usually has none. Actually, usually has none. Oxygen has how many protons? 8. And usually has how many neutrons? Usually has 8. It's usually oxygen 16. Carbon has how many protons? 6. Usually has how many neutrons? 6. And then helium has how many protons? 2. And usually has 2 neutrons, right? So that. Now we can look at our periodic tables to actually get a sense of what the most common isotope of each element is. So yeah, get out your periodic table. Now, what I want to look at for each of these is I just want to make sure that what we said was the most common isotope, what we said was the most common nucleon number, is in fact accurate. So if I look at hydrogen, this particular periodic table says that the average atomic mass of hydrogen is 1.0079, right? So that must mean that hydrogen 1 is by far the most common one that we encounter. Yes, there are some heavier ones, which is why the average atomic mass is a little greater than 1, but it's so close to 1 that, yes indeed, right, the most common isotope of hydrogen must have no neutrons at all. A single proton with an electron. Oxygen's atomic mass, average atomic mass is 15.999, right? So yes, oxygen 16 must be the most common one. Carbon is 12.011, so yes, carbon 12 is the most common, and helium is 4.0026, so yes. So I'm actually going to ignore hydrogen. Hydrogen, I mean, it's just a proton usually. Like, we don't need any strong nuclear force to keep it stable. We don't have two protons that we have to counteract repulsion of. So I'm going to get rid of hydrogen. Let's just take a look at a few heavier things. Can somebody pick an element who has 20-something protons?
Chromium.
Chromium. Is that Cr?
CR, yeah.
Okay. So find chromium. Wait, it's not 20. What is it?
24.
24. And what is the most common isotope of chromium, do you think?
52.
Probably 52, because the periodic table says 51.996 is the most common mass, or is just the average atomic mass. So yeah, probably 52. Let's do something in the 30s.
Arsenic.
Arsenic, is that AS?
Yes.
You're just picking the ones that have like misleading symbols, right? But you didn't get me that time. All right, arsenic had how many protons? 33. And what's the most common isotope, you think? Probably 75, because the average atomic mass is 74.922. All right, let's pick something in the 40s, and then maybe we'll do something in the teens after.
Silver.
Molybdenum. All right, is that MB?
Oh.
Oh, you got me.
What? Oh, I was only
You got
saying-
me?
I said it because it's 42, but what?
Kudos to you, you got me. All right, and then 42 protons. You got one that I got wrong. And most average, or the most common isotopes, probably 96. All right, let's do something in the teens.
Antimony.
Antimony, I know that one. It's SB.
That's 51.
51.
Wait.
I don't think it's teens.
But I had you with that.
Well, you didn't, and you were wrong. All right, so in the teens. Argon? Oh, you're being kind.
Yeah.
All right, so argon has how many? It's got 18 protons, and what's the most common isotope, you think?
40.
Probably 40, right? All right, so let's take a look and just make sure that this exercise is consistent with our graph over there. So all of our lighter things had at least the most stable, but at least a very stable isotope that did actually have the same number of protons and neutrons. Now, I don't, we could zoom in and it actually probably looks like the green and red are a little above the n equals z line down here, but whatever, it's like very close. And then arsenic, which isn't all that much heavier than oxygen, like a little, maybe twice as big, a little more than twice as big as oxygen. Arsenic does in fact have more neutrons than protons. It's got 22 neutrons, 18 protons. And that's very stable, right? So we do see that there's relatively more neutrons for protons here. And then as we get heavier and heavier, that increases, right? So chromium has 24 protons, and what, 20, what was it? 28?
Yeah.
28 neutrons. Arsenic has 33 protons and 44 neutrons. Molybdenum, 42 and 54. So as we get bigger and bigger, as we get more and more protons, we kind of need disproportionately more neutrons. All right, questions before I make an attempt at having that make sense? Miles, do you have an attempt?
No, I was going to ask, why would more protons make a nucleus more unstable if they're all attractive forces?
The strong nuclear force is always attractive.
Yeah.
And the strong nuclear force does exist between a neutron and an adjacent neutron, a neutron and an adjacent proton, and a proton and an adjacent proton. So you're right about that. Right? All three of those combinations yield an attractive force, but we still have this electrostatic force, which means if we have two protons adjacent to each other, they want to get the heck away from each other, right? Because they both have a positive charge, so there's a very strong repulsion. Well, the very strong repulsion might not actually be as great as might now. It is going to be greater than this strong attraction, because was it in here that I made the bet?
You made the bet.
So I made the bet, which I lost because I was dumb. But what I was right about is that there is no such thing as helium-2, right? Because there is no such thing as two protons that can stay together without the aid of at least one neutron right next door. Yeah.
Did I say protons? I meant why more neutrons would make it unstable.
Alright, well, I heard proton.
Did I say
You said-
I think that there's
Oh,
a disconnect between
That
what
was,
you
that
said and
was
what I
much
heard.
less, my
yeah.
question was much different than what I meant.
Alright. So let me proceed, and then if I haven't answered your question, let me know.
Okay.
Let's pick on. I like carbon. I think I said that last time. So I'm gonna draw carbon. I'm gonna pretend that it's two-dimensional. So let me draw. I need 6 protons and 6 neutrons. All right. So proton, neutron. Just start throwing them in here. And at some point I'll have to add them up to see how I'm doing. I feel like I have too many neutrons. I have 5 neutrons. Oh my gosh, I have 6 neutrons already. Only 3 protons. All right. Maybe I can put a proton over here, and maybe a proton over here would be okay. Is that right? 6 and 6? Okay, great. Now which proton do you think is happiest? Let's say 1, 2, 3, 4, 5, 6. I want to go with the happiest one. Which do you think's happiest? 4. I heard 4s and I heard 1s. I'm gonna look at 1 first, and then we can look at 4. All right. So proton number 1 is feeling a strong nuclear force from how many nucleons? Probably just 2. Right. The strong nuclear force is very strong and it's attractive, but only at ultra short ranges. So this proton is being attracted to this neutron and this neutron pretty strongly. How many protons are repelling this guy? Yeah, well, 5. And for this particular proton, all 5 of the other protons are pushing them that way. Right? These and maybe those are stronger than the neutrons are pulling. It doesn't really matter. What does matter is that the proton can feel all the other protons, but can only feel neutrons that are right next to it. All right? The strong nuclear force is a much shorter range force than the electrostatic force. So apparently for carbon, right, we can make an arrangement that's pretty stable though with 6 and 6. For stuff that's heavier, right, let's add some more. Let's keep adding some stuff. I'm just going to keep adding like a proton and a neutron. I'm only going to kind of add over here. So let's add maybe a proton here and a neutron here and a proton and a neutron and a proton and a neutron and a neutron and a proton. How many neutrons are still attracting this proton? Still only 2. How many protons are repelling it? More, right? More. So as we get bigger and bigger, right now I could add some neutrons next to this one also, right? So maybe we should talk about a different one. But I think some of you are kind of getting this, that as we keep adding nucleons, right, the repulsive force increases, but the attractive force doesn't necessarily increase. For instance, proton number 4, right? I didn't add any neutron next to it, I don't think. So I didn't increase any strong nuclear force, but I did increase electrostatic repulsion, right? So this proton, I think, is less happy than before, right? Even the ones in the middle, not just the ones at the edges, right? So it's really because the strong nuclear force is a much shorter range force that we have to add extra and extra and extra neutrons, right, in order to keep those guys pretty happy. And so maybe we need 5 extra neutrons with the extra 6 protons that we just added. I don't know. Well, actually, I guess I could know. Well, how many protons did I add? There were 6 originally, and here's 7, 8, 9, 10. Did I only add 4? Okay. Who has 10 protons? Neon. How many neutrons does neon have? 20. 20? Alright, yeah. So maybe I need to get a little bit bigger before this becomes as significant as I'm saying. Alright, so these stable nuclei diverge from neutrons equals protons because of the longer range nature of that electrostatic repulsion. This actually is a big deal. We're going to come back to it, but that's probably enough for today. Liam?
So why are big things like less stable? Why can't you just
Why
have
are big
ton of
things
neutrons?
less stable? So anything heavier than uranium?
Yeah.
heavier than uranium, why can't we get stable with extra neutrons? You know, there's like special numbers of electrons that kind of give chemical stability, and like, was it the first energy level has like 2 electrons, and the second energy level has like 8, and then the third one has like 12 or something like that. I think so. No, I think the D level is 12 and the F level is 16, I think. I'm pretty sure. I'm like not 100% sure, I'm like 99% sure. So there's magic numbers of electrons that for reasons that I couldn't even, I could start to tell you, but I wouldn't get very far. There's magic numbers of nucleons also. The smallest magic number, anybody want to guess the smallest magic number? Maybe some of you have heard this. No, well, 0. 37. Mr. Technicality today. No, it's actually, I think it's intuitive based on what we've learned already in this unit. What's the smallest arrangement of nucleons we've seen that seems to be very, 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 very happy?
2.
Not 2.
4.
4. Patrick, what are you thinking of that nobody else is thinking of?
Alpha particle.
Alpha particle, right? That assemblage of 2 protons and 2 neutrons is so stable that it's like one of the 3 types of nuclear decay that we talked about. It's a very common type of nuclear decay because those 2 protons and those 2 neutrons are so happy together. Right? That's such a stable arrangement. So where am I going with this? Liam, there are there are special numbers of protons and neutrons that might be stable, that are heavier than uranium, but we haven't put together something big enough yet to get there. So sometimes we hear like an island of stability referred to, and we do invent elements every few years. Like we jam together something slightly heavier that lasts for a few nanoseconds. We are pretty sure that eventually we're going to find some that are a little bit more stable if we hit those magic numbers. And the magic numbers are not, that's not part of this course. I wouldn't mind talking about it more, but it's really not part of this course. So anyway, let's I think I've said all this, but let's just catch up. So that diagram showed that our stable nuclei got further and further away from that neutron equals proton line. And again, that's because the repulsive force between protons is a longer range force than the attractive force between nucleons. And then, and actually I thought this is where Liam's question was coming from, but probably not, since we haven't looked at this slide yet. Eventually, we actually can't cut it with extra neutrons, right? Eventually, we do just get too large to let extra neutrons get us stable. 83 protons is actually about as stable, or the biggest stable thing we can get. Who is that? Yeah. So I actually kind of said uranium earlier. Uranium, there is no stable isotope of uranium. So I think bismuth. Yeah, bismuth is apparently the largest number of protons that we can add enough neutrons to keep it pretty happy. And I think, what do we use bismuth for? I only know one use of bismuth. For what? For leaks? I don't think, not that I know of. Yeah?
So a question about the state.
Oh, come on, let me finish my thought. I'm going to forget it, but I'll finish it. No, the thing, that's, what's the pink stuff you eat when you're sick?
Pepto-Bismol.
Yeah, Bismol, right? Bismol comes from bismuth. And in fact, if you don't want to spring for the brand name, the generic stuff that I bought is just called pink bismuth liquid. I mean, that doesn't prove that bismuth is stable, but especially when we're like throwing up and like sick, or we don't want to put something that's radioactive in our stomach. So apparently that is, there's at least some stable isotopes. All right, Ryan, go ahead.
So, for the mass numbers, if it's in brackets, does that mean it's unstable? If it's not in brackets, does that mean it's typically
I don't think so. I think the ones that are in brackets on this particular periodic table are ones that are not naturally occurring. Do I mean that? Let me look around a little bit. So it's not everything that's heavier than bismuth that's in brackets, but it is most things. The only exceptions I'm seeing are thorium, protactinium, and uranium.
How about like technetium?
What's that?
Technetium's 43 and it's in brackets.
Yeah. It probably says on here if we read the bottom. No, it doesn't say. Yeah, I can't. Oh no, yes it does. Come on, you just gotta read more carefully. Yeah. No stable nuclides and are represented by the element's longest lived isotope. So there is no such thing as stable. Right? It's all relative. We said all mass is unstable. But stable isotopes are ones that hang around pretty long before they decay. In fact, I don't want to have this discussion. Let's talk about half-life and then have that discussion, because then I can use better vocabulary. Okay. So we did say last week that all of our radioactive decays are both random and spontaneous. In addition to those observations, we also want to be able to talk about the rate of decay. And a really important thing about that, and this is I think the first time this year you see me use this word, the rate of decay decreases exponentially with time. I don't think we've seen an exponential thing in this course yet. All right, so this exponential decay rate is what we want to devote much of the rest of today to, and then you will actually see this some more next year. All right, so we do have our one defined objective for today, which was radioactive half-life. Half-life is an amount of time. Now, this is not our official definition, but it's the first way I want to introduce it to you. It's the time it takes for half of a sample of radioactive nuclei to decay. All right, so if we start with 15 million, unstable uranium nuclei, then the half-life is how long it takes for 7,500,000 of them to decay into something else. Not that complicated of a thing. Yeah, Liam.
It's not really related to this, it's kind of related to this. But when you go through beta decay, how does that help stabilize a nucleus? Because
Well, sometimes, as we saw on the stability curve, sometimes we have too many neutrons for protons, right? That was the red above the green, and sometimes there's actually not enough, and that would be below the green. But that actually might be something that we're better served to look at with topic 7.3 once we look at mass's role in this. Yeah, Miles.
Why are the presence of more neutrons than necessary destabilized?
Why can we have too many neutrons?
Yeah, because would they all just attract each other and just hold the whole thing together more?
My first thought, and I don't usually get thoughts this quickly, so I'm a little concerned, but my first thought, I kind of wish now I hadn't erased what I drew before. If this is that proton number 1 that we were kind of analyzing, so there is a whole bunch of stuff over here, right? But what if we do put 3 neutrons right over here, and maybe there's a proton here, and maybe there's a neutron here? Aren't these 3 neutrons are going to pull super hard to the left, this proton's going to push it super hard to the left, and then this neutron, yeah, it's going to pull it to the right, but why wouldn't that guy just fly right off if there's too many forces like one way and not enough the other way? So without this neutron here, maybe it's happy, but then if we get too many neutrons, and that's my first thought, and I don't know, I want to think of that a little bit more before I'm convinced that it's a valid response, but it seems all right. All right, so radioactive half-life is a time. Our technical definition is not based on a percent of the nuclei decaying. It's the amount of time for the activity to decrease by a half. And when we say activity, we mean radioactivity, right? So this is telling me the activity, right? Every time this clicks, it's because it's catching a decay product, right? A decay product is hitting it. If we had a truly radioactive source, like we would just hear noise. We wouldn't even hear distinct clicks. then we'd have to look at the needle to know what the activity was. But the activity is like how many decays per second. So it really is the rate of decay. So the half-life is the time that it takes that activity, that number of decays per second, to decrease by 1/2. All right, so that's all that half-life means. Let me try and go a little bit quick through a few observations here. I've said a few times, including just like a couple minutes ago, that all matter is unstable. The most stable thing that I can think of that's matter is a single proton, and even a single proton eventually decays. Just matter is inherently not the most stable form of energy out there. Now, a proton is very, very, very stable, right? So stable that we don't have a great grasp on its half-life, but we're talking something like 10 to the 33rd years. The age of the universe is like 10 to the 10th years, so that's like the age of the universe like cubed, for half of the protons in the universe to decay. So a proton actually is quite stable. Now a neutron, on the other hand, all by itself is extremely unstable. Right, a free neutron, a neutron that's just kind of hanging out, sitting in the room, 10 minutes, it has a 50-50 chance of decaying into something else. Neutrons being bound up in the nucleus, the neutrons feeling this strong nuclear force, actually keeps them stable. Right? Neutron in the nucleus, stable. Neutron outside of the nucleus, extremely unstable. So everything's unstable, right? But we need some measure of how unstable, and the half-life is probably our simplest measure of that. Yes?
What about electron?
Electron, I mean, it's matter, so I don't think it's all that stable. But my first guess would be somewhere in between proton and neutron. So somewhere in between 10 to the 33rd years and 10 to the negative 4th years.
And you're probably.
Yeah, that's a large range. I'm probably right. I'm probably right there. Maybe I can win my bet back. Right, but I mean, more commonly, half-lives for our nuclei range from like minutes to billions of years. In fact, I mean, if it's more than billions of years, that's when we start to call it a stable isotope, right? Not completely stable, still could decay, but it's going to take more than billions of years for half of our sample to decay. So we want to spend a few minutes looking at what we call decay curves, and then we will work with half-life a little bit quantitatively, and I'll show you a few different ways to do that. All right, so what do we have here? We have on the y-axis, it says proportion of parent atoms remaining. I probably prefer that this said nuclei, but I'm okay with atoms, right? And at a time, and then we have time on the x-axis. So at a time of 0, we have 100% of our atoms remaining. Like nothing has decayed yet, right? That's just when we're going to start keeping track, right? And apparently, our parent atom, the pre-decayed atom, right, is being shown as these black dots. So after one half-life, which on this is like the simplest decay curve that I have for you. One half-life is just 1 unit of time. After one half-life, right, we shouldn't have 20 black dots and 0 red dots anymore. Half of those should have decayed. So instead of 20, we have 10 of our parent nuclei, and then 10 of our daughter nuclei. The daughter's the thing that, like after the decay, we call that the daughter nucleus. After another half-life, we should have half of the 10 still there. Right, so now we have 5 of the parent nuclei and 15 of the daughter. After another half-life, we would have half of that amount. Now we can't really have 2.5 of a nuclei, right? This stuff doesn't work with 20, a sample of 20 anyway. We need millions of nuclei for this stuff to really be accurate and work right. So every time a half-life goes by, we cut the number of the original unstable nucleus, the number of those in half. Yeah, Patrick.
So for like carbon dating, do they like count the amount of carbon in there and then what that element is to?
So I'm gonna just make a note up here and then answer that in a few minutes. So for carbon-14 dating, like what do they count? That's kind of your question, right?
Yeah.
I'm gonna come back to that in a few minutes. Isaac?
So if it keeps thinking half
Yes.
each time, it never reaches 0, right?
So does it ever reach 0? Well, I said that this really only works if we have like millions of